Okay, so the chalks. Oh, yeah. So let me start by recalling what. Oh yeah, chalks. Thanks. Yeah, thank you. By recalling what we did in the last lecture. So let's recall. So we had we started discussing basically divisors. So it was all about divisors. So basically, X, a compact Riemann surface, right? And then we defined the group of divisors to be the set of all maps B from X to Z, where this X has this D has finite support, right? D has finite support. So this is the so this is an abelian group under addition. So A of D1, D2, the addition goes to D1 plus D2. You can easily check that this is again a divisor. And the notation that we used for divisors was something like this. The notation was D equal to sigma D of P times P. Sometimes I may not even put the dot because these P's are just basis elements for the space of for this free abelian group of divisors, and just write P belonging to X, right? So this is a finite sum because this D is 0 on everything except for a finite number of points. Then we define this degree of a divisor. Degree from dx to z, right? So this is a group homomorphism that we defined like this. So this was degree of D is sum D of P. P belonging to X. So this is a group homomorphism, right? I mean, it's clear. Group homomorphism. Right? And we define the kernel of this group homomorphism to be just degree 0 divisors, right? So D 0 of X, this is the group of degree 0 divisors. Degree 0 divisors. This is basically kernel of this degree map. So this is a subgroup of all divisors. So we have this. If 0 X is an abelian subgroup because it's a kernel of a homomorphism. So this is inside dx, right? And I said that actually this map degree here, this map actually splits, but not canonically. There's no canonical splitting, but it splits non-canonically. Right? And in fact, to define the splitting, but what does the splitting mean? It means that there is a group homomorphism in the other direction. So let's call it maybe S, just very temporary. This splitting is obtained by, you have to fix a point P. This is so arbitrary, right? It's not canonical. So fix P belonging to X, and then you get this S in the following form. So S of N is equal to this divisor, N times P. And then you can check that if you go this direction and come back, so if you go this direction and come back, you get identity. So you just check that degree composed with S is equal to identity of Z. Because if you take degree of this guy, such divisors, you're going to get N again. Degree of 60. So this sort of gadget implies that actually there is not much a distance between these divisors and degree zero divisors. The codimension is 1. It's like linear algebra. When you have a linear homomorphism into the ground field, this always gives you decomposition. And in this case, gives you a non-canonical decomposition. And you can prove here that dx is isomorphic to div 0 of x. Dx sum z. I mean, this is just bear in mind. I mean, this is not so important for us now, but it's something you know that. Okay, and then we defined a very important class of divisors called principal divisors. I'm just all recalling from last lecture. So for any meromorphic function, meromorphic, and let's say non-zero, we define the divisor of this meromorphic function, div f, to be the following thing. It's defined by definition, it's defined to be some order of f at various points p times p, where p belongs to x. So basically, this measures all the poles and zeros and labels them with the order of the pole, order of zero. If it is a pole, it's negative. If it is a zero, it's positive with that order. Otherwise, it's zero. At all other points that are not poles or zeros, this is just zero. Okay? Now, we proved the theorem. Actually, I gave 2 proofs, you remember, that the degree of such divisors is 0. Sum of orders is equal to 0. So since a sum of order of E f is equal to 0 for all f meromorphic, this implies that these divisors of meromorphic functions are actually degree 0. These are degree 0, right? So, and then I define principal divisor to be exactly such divisors that are obtained as divisors of meromorphic functions, right? So let me now just last recall today. So I think we had a notation P div of x this is the set of all divisors of the, the divisors of the form div f. The f is meromorphic. Okay. And so what we have then, if we put everything together, we can put everything together in one sequence, which is principal divisors. Right? I mean, this is, I just don't want to write it as a sequence, I just write inside the divisor 0 of x, and this is inside all divisors. We have this, so have this in mind all the time. This, and I said that the distance between degree 0 divisors and principal divisors is a very subtle matter. I mean, to understand which divisors are actually a principal or which degree 0 divisors are principal is the content of Abel's theorem that we will prove. But for now, let me just check Actually, I think we did check that for any divisor. So I gave several examples. So with any degree zero divisor, okay, so let me write any B belonging to B zero of the Riemann sphere, actually, any given, there exists a meromorphic function such that actually you can say B is equal to divisor of. So in other words, for x equal to c hat, actually there is no distance between the two. Principal divisors are degree zero divisors exactly. But we'll see that actually for all other Riemann surfaces of genus G bigger than or equal to 1, they are different. But not equal if genus G is bigger than or equal to 1. So the genus, if the genus is bigger than or equal to 1, they are not the same. We will prove that, but we'll see that. But for now, so we defined, okay, so today now, so we are going to consider another class of divisors. We call it canonical divisors. So what is a canonical divisor? So these principal divisors are divisors of functions. Now, if we take a meromorphic one form, then we do get canonical divisors. So let omega be a meromorphic one form. Okay. So locally, of course, we can write. Locally, we can always write this as omega equal to f of z is z. This f of z is only defined in a coordinate neighborhood and is a meromorphic function, right? So using this presentation, we can define divisors of omega to be a sum order of omega p times p belonging to S, where order of omega p is order of this function that defines your one form, meromorphic one form for you. Right, so we define this V. And then what are canonical divisors? The canonical divisors is the set of all divisors that are divisors of some meromorphic one forms. So the notation then is K div of X is the set of all divisors of omega such that omega is a meromorphic one form. Okay. So now we have one extra element to add to this, but we should see that this is basically these canonical divisors are not inside div zero of X. They are just divisors. There is an interesting relation between these things that we will see soon. So, but these are canonical divisors. Okay. So let's look at some examples now. So of such divisors, right? So let's look at so Riemann sphere for us is like what? Is like a discrete topological space in general topology, right? any example, any theory, you can check it against discrete topological space or trivial topology. Either two open sets or everything is open. So Riemann sphere plays such role for us because everything you can easily test for that. I mean, it's kind of, okay. So example, let's take x equal to c hat. So can you now show me a canonical divisor here on the Riemann sphere? So all we have to do, you have to find a meromorphic one form and then take the divisor of that meromorphic one form. So we have to now give a meromorphic one form on the Riemann sphere. What is that meromorphic one form on the Riemann sphere?
1 over z is what?
1 over z dz works, but why you start with 1 over z? Can you give me something even simpler? Just dz. Exactly, just dz. So 1 over z dz is also absolutely fine. But there is something simpler. Even here is omega equal to dz. So this is a meromorphic one form. So where are the poles and zeros of this guy? So the only place that we don't understand this is at the point infinity. So we have to understand the point infinity. And for that, we just choose coordinate w equal to 1 over z. So this is the coordinate at infinity. So this gives me z equal to 1 over w. And then if you write dz is equal to minus dw over w squared. Okay. So this shows that the order of this function, the order of this dz at infinity is equal to minus 2, because there is this minus 2, right? So this is equal to order of, I mean, minus 1 over minus dw over z squared, which is equal to minus 2. So the divisor itself, right?
Isn't it over w?
Oh, this is over w squared. Yeah, of course. Yeah, we moved to 0. Yeah. Very good. So this is minus 2. This is not z, by the way. Minus 2. Okay. So now we can say what the divisor is. So the divisor of this guy, divisor of this one form, meromorphic one form dz, is minus 2 times infinity. Because there is no other zeros or poles, this guy. At all other points, he is absolutely pole-free, zero-free. Okay? Okay, now in general, of course, we can take, you can take omega equal to f of z dz, where this f of z is a rational function. So this f of z is a rational function, and dz over qz. So this is a rational function. Okay. So okay, and then there is a simple exercise to do actually working with this. So exercise is to show that divisor of such things again is equal to minus okay, so here I've got, from here you get that degree of this divisor. So let me write it. Degree of divisor of dz is equal to minus 2. Okay. And in this case, we can write, so actually it's better I write it in a different form. I'm going to write it in the form as already product decomposition. So let me write it as product of z minus lambda I EI over I, and then there is dz. Okay, well, lambda I is different from lambda j, right? So if you want to take the divisor of this guy, then you're going to get zeros here. So this is sum, and the zero has degree, has order EI for lambda i's. So this is EI times lambda I mean I from 1 to n. But then there is you have to be worried about point at infinity. So if you look at point at infinity, you're going to get -2 minus actually sum of EI lambda I from 1 to n. Suspicious about that. Okay, yeah, -2 plus sigma EI, sorry, I mean, this has to be a number times infinity, right? So I need, yeah, this is correct, yes, infinity. Okay, so the only thing that you have to think a little bit, to do a little bit of calculation is the point at infinity. How do you go about finding the things at infinity? You just change z to 1 over w, and then you're reduced to working around 0. Then you're done, okay? So this is the divisor. And again, let's look at degree of this divisor, right? So what is the degree of this divisor? So when you compute the degree, you see that there is this sum EI -2 minus sum EI, again is -2. So in fact, this, if you do the exercise, you have proved that for any divisor, the degree is -2. So i.e., not for any canonical divisor. On C hat, canonical divisor E omega. This shows that degree of this guy degree of this divisor of omega is -2. So -2, what number reminds you of -2? What number is -2? Well, -2 could be anything, but there is something that's pertinent to this discussion.
Euler characteristic.
What's that?
The Euler characteristic.
Euler characteristic, but
With a minus.
with minus sign, and that's it. So this is equal to minus Euler characteristic of C hat, but that's not an accident. It's a special case of a very general theorem that I will prove now, but not an accident. Or you can say this is the, I don't know, 2 is the second element in Mendeleev table. It's minus. You know that element, right? Helium. Helium, yeah. Exactly. It's minus helium. So you can say, yeah, I mean, the degree of a canonical divisor is minus the order of helium. But that's not true for other Riemann surfaces. So now let's look at another example. Check this conjecture. Another example. Let's take x equal to c over lambda. This is the complex torus. Okay. Now, can you give me now a canonical divisor on this torus, on the complex torus? So you need a meromorphic one form on the complex torus. Obviously, I mean, you can take omega equal to dz. We check that this dz exists on the plane, but because it's invariant under the lattice, it goes to the quotient. So this is one. But this is a actually holomorphic one form. It has no zeros or poles. So this is actually holomorphic one form. So in old terminology, they were called abelian differentials of first kind. Abelian differentials of first kind. This is what we call holomorphic one form. Okay, so what is the divisor of this guy? It's just zero. There are no zeros, no poles. This is smooth everywhere on the torus. There are no, and then,
What's an abelian differential?
huh?
What's an abelian differential?
It is this, something like this. Abelian differential is a holomorphic one form on a Riemann surface.
Okay.
This is called the abelian differential in old terminology, in honor of Abel. Okay, so this is abelian differential of first kind, and this is this one, and our divisor. So what is degree of divisor of omega now? Well, this is obviously zero, but what is zero has to do with torus. Now, what is the connection?
The same thing.
The same thing. It's again Euler characteristic of the torus, right? It's but minus. I want to write minus Euler characteristic of the torus. Yes, C over lambda, which is zero. By the way, the fact that omega dz is a holomorphic one form, I mentioned this. The dimension of a space of holomorphic one forms is the genus of the curve. That's one of the things that also we will prove soon. Okay.
So the Euler characteristic is 2 minus 2g.
Euler characteristic 2 minus 2g. Yeah.
Okay, and g is 1.
G in this case is 1. Exactly. Yeah. Exactly. The Euler characteristic of torus is 0. For a sphere is 2. And then for higher genus, they drop 2 by 2. They go to minus infinity. It's minus 2, then minus 4, minus 6. They go by even numbers, goes in. It's very important. Okay, now let's see what we can do with this holomorphic, meromorphic one forms. Any questions about meromorphic one forms? Okay, so now let me prove some little lemmas and then we use them soon. So lemma is let omega 1, omega 2 different from 0 be meromorphic one forms on X, right? So then there exists a meromorphic function f on M of X such that omega 1 is equal to f omega 2. So if you take two meromorphic one forms, the second one is non-zero, is not identically 0, that means then you can write omega 1 as multiple of first one with a function.
So omega 1 might be 0.
Huh?
Omega 1 can be 0.
Omega 1 can be 0, and in that case, the question is easy because you can take f equal to 0. But in general, we have to see. So proof. So choose local coordinates. So to define f, so we just choose local coordinates. And then in that local coordinate, you can obviously write omega 1 equal to f1 of z dz, where this, I just write h1. h1 of z dz, where h1 is meromorphic in that over u. And I can write omega 2 equal to h2 of z dz, right? Is also meromorphic. Now you notice that in that local coordinate, I can obviously write omega 1 equal to h2 z dz times h1 z over h2 z. Right? They cancel. This is non-zero because the guy is non-zero, and so this I declare to be my f. But this f now you have to be careful. This f is only locally defined now, right? This f is only locally defined. Now we just check that this f is independent of choice of coordinates, right? Next step is check that f is independent of choice of coordinates. So how can we check that? Well, we have to change coordinate and see if the definition of this f, which is the quotient of h1, h2, remains invariant. So if you go to a new coordinate system z equal to g of w, for example, then in this coordinate system, say u and w, or let's put v and w, you can certainly write omega 1 is h1 of, you just replace g by that, g of w, d of g of w. So this is h1 of g of w. Then we have got g prime of w, dw. Right? And similarly, you can do the same thing, omega 2 is equal to h2 g of w, dg of w. So this is h2 g of w, g prime of w, dw. And so you notice that, so in the new coordinate, we have to divide this by that, right? This is the new thing here, we have to divide. If you divide, you see this probably or potentially offending factor, they cancel each other. The factor that depends on coordinate, they cancel each other. And so you get omega 1 actually equal to h1 of g of w over h2 of g of w times h2 of g of w. And then omega 2. Okay, I mean, this function is independent of choice of coordinates because it's exactly the expression of the function where you change coordinates from one coordinate to another. So this is okay. So if you want to, I mean, this is kind of calculus question. Like you can test your calculus student. If you give this question to your calculus students, those students who are smart would say this. Well, I just define omega 1 over omega 2. Omega 1 is equal to omega 1 over omega 2 times omega 2. And omega 1 over omega 2, you just write f of z dz divided by, I mean, f2 of z dz times omega 2, and dz's cancel. Smart students would cancel immediately, and then you say, oh, this is what is the problem? So dz's cancel. Oh yeah, I mean, this is of course funny idea, but essentially that's what's going on. This is really what's going on. So it's like divide dx in calculus, where you play with those things. Okay, so that's good. But this has very nice corollary that this result is very simple. It's not a problem at all, but it has a very nice corollary. The corollary is the following. That if you have two canonical divisors, if D1 and D2 are canonical divisors, then D1 minus D2 is a principal divisor. Yes. 1 minus D2 is a principal. Principal divisor. Okay. So let's see how this works. Again, proof is not difficult, it's just a corollary about it. So because D1 is canonical divisor, you can write D1 as divisor of one meromorphic bond form, right? Divisor of omega 1, you can just write it like that, and D2 is equal to divisor of omega 2, right? And then we are assuming that D2, this omega 2 is not 0, so here write the omega 1 equal to F omega 2. Then we use the following formula. Divisor of, if you have a meromorphic bond form multiplied by a meromorphic function, is equal to divisor of F plus divisor of omega. Of course, we had a similar result for product of two functions. Divisor of fg is equal to divisor of f plus divisor of g, right? So this you have to compare with divisor of fg is equal to divisor of f plus dg. So it's exactly like that. And the proof is the same. So once you use that, then we can just say, okay, what is d1 minus d2? So d1 minus d2 is equal to divisor of omega 1, which is omega 1 is f omega 2, right? Minus divisor of omega 2. If we use this fact, this is equal to divisor of f plus d of omega 2 minus d of omega 2. And you see that they cancel, and you're left only with d of f. Divisor of. And this is a principal divisor, i.e. the difference is a principal divisor. So, okay, so the difference of, okay, notice that the sum of two principal divisors is not a principal divisor, not at all, because so the difference here, but the sum need not be principal. I mean, need not be canonical. I mean, need not be canonical. I mean, we saw that I mean, this need not be canonical because if this is divisor of omega 1, this one is divisor of omega 2, we cannot multiply these meromorphic bond forms in any reasonable sense. You multiply, you get 0. because there are one form, you get zero. And if you don't use exterior product, you use just some non-exterior. We don't have those objects yet, and we will never use those. So that's not the form anyhow. So definitely, I mean, this is not true. But this corollary implies that actually canonical divisors is a equivalence class of principal divisors inside the set of all divisors. So let me write it this way. So corollary implies that k div of x is the yeah, it's how to formulate it? What is the best way to? Yeah, the word is coset. Yeah. So it's a coset of the set of, I mean, the subgroup of principal divisors in all divisors of X. Okay, so basically k div of X is equal to p div of X plus some divisor. And these guys, yeah. Okay, so let me erase this because this leads to more confusion. Just the word coset is good, I think. Yeah. So the coset means that we just take this subgroup and translate it by one element because it's abelian, so we just translate instead of multiplication, we use addition. So that's I'm a bit uneasy about this, but I think this is correct actually, But I have to think about it. Let's think about it over the break. I'm a bit. I mean, the statement is correct, but what it really means, how to write it, I'm not so sure now. So I will think about it over the break.
Is that the statement K div is a coset of?
Is a coset of the principal divisors.
Okay. With respect
in the group. You see, this is a subgroup for principal divisors. Is inside divisors. And what is a coset? Coset really is, we just take this and add all possible elements from the group of divisors here. That's the definition of coset, right? We just take all translates of this, and that's it. So that's anyhow. So this is something I still from group theory, from basic group theory. I have to think about it to someday produce it in a better way. Maybe. So then, okay, anyhow, but one thing that this corollary implies also that the degree of a canonical divisor is well defined, right? So any two canonical divisors have the same degree. So this is a really good corollary. Any two canonical divisors have the same degree. I mean, why? Because if you take two canonical divisors, right, D1 minus d2. I mean, this is equal to divisor of some meromorphic function, right? For some f. And degree of this guy is 0, so it means that, so this implies that,
Sorry, degree of what is 0?
sorry, I'll tell you, this degree of divisor of f, but these principal divisors have degree 0. This is the theorem that I mentioned at the beginning of the lecture. This is 0. So degree of d1 is equal to degree of d2. It doesn't matter which, you have many choices for canonical divisors, but any two of them have the same degree. Is that what you asked? Okay. So now I want to prove that actually degree of this any canonical divisor is minus Euler characteristic, and then we will verify what we wanted to do. Okay. Okay, I think I can do it in 5 minutes, hopefully. So. Okay. Now let f from x to c be a non-zero meromorphic function. Okay. So then what we do, I mean, so immediately we can get, of course, from here, we get this map F, capital F, which is same, but we interpret it as going into the Riemann sphere. So this is a holomorphic map. Immediately we get this. So let's assume that it has degree of F equal to D. Then by Riemann-Hurwitz, formula, we can just say that the Euler characteristic of X, did I write Euler? Yeah, is equal to degree of F, which is D, times Euler characteristic of C hat. But there was a correction term because there are possibly some ramification points. It's not just a default covering in general. There could be some ramification points, and those contributions give us minus sigma E belonging to X. Now I just use a notation now, which is maybe is new, but let me just check with you guys. So this VP or VP of F is the something we call multiplicity of F at P, right? So we also denote by this multiplicity of F at P is another term for it is the valuation of F at P. It's a valuation. That's why we use V. It's a valuation of F at P. And this is a formula that's Riemann-Hurwitz formula, celebrated Riemann-Hurwitz formula. Okay, so I mean, this guy, of course, Euler characteristic of C hat is 2. From here, if you do the simple algebra, you get the E belonging to X. All valuations of F at different points minus 1 is equal to 2G minus 2 plus 2 degree of F. Okay. So what's the importance of this? I mean, this is a very simple application of Riemann-Hurwitz formula. Why we want this now? Doesn't look very important to me right now. But what is coming next right now is absolutely fundamental. So now, so we are in the same setup now. Let eta be equal to d star of f. I mean, what is this? F star of dz, where dz is a meromorphic bound form, is the canonical meromorphic bound form on a star.
What's that stuff?
Huh?
What's that stuff?
Oh, I'll tell you. We have it before. We had it before, but I'll tell you. Dz is equal to, I mean, the canonical bound form. Canonical, yeah, no, shouldn't use canonical bound form. It's really, it's just what it is. It's just dz. Okay, so your question, what is f star? You see, I told you anytime you have a map between Riemann surfaces, x to y, very generally, you can pull back objects from here to here. So f star, first of all, you can pull back meromorphic functions on y to meromorphic functions on x, right? Meromorphic functions on y. You can just write to put it into meromorphic functions on x, and this is a field map, so it's definitely going to be an injection because this map is a surjection anyhow. But there's more. You can also pull back forms, right? You can pull back forms f star of omega, which is f star of, if you write in some coordinate, maybe f of z dz, for example, in some coordinates, write it like that. This is nothing but, what is it? This is just f of z. So it's a pullback of this time times d of okay, so now this is not good, so I should put another, so f of w and d of f of w. You see, I'm just thinking of this is the one form, and w is a coordinate on x, okay? Okay, so on y, so yeah. I mean, this is very general. You can pull back forms, and you can pull back functions. You can pull back all of the wrong complex, actually, so that's what it is. And that's what we are using. So there is this meromorphic bound form on x. As soon as you have a meromorphic function on x, as soon as you get a meromorphic function on x, you can pull back this God-given one form dz on the sphere, and you get a form. Now we want to show that degree of this, degree of eta is actually equal to minus Euler characteristic. So this is the most important calculation of this hour. Right, so we want to show that degree of, so the goal now, which is true actually, degree of eta is equal to minus Euler characteristic of this. So we're going to prove it in the next lecture. So once you do that, then, okay, so then we have some and start. Basically, once you do that, you are at the base of the Everest camp, and then the ascent starts after that. So you must bring in a lot of gears and